Hello, my name is Quang Trong. I will talk about our effort in modeling of waste heat-based lunar ice extraction process. And this work was a collaboration from Advanced Cooling Technologies and Honeybee Robotics. For introductions, the presence of water ice was spotted in the cold regions of the moon. However, significant power is needed to supplement the water ice from the regolith, and that would roughly be 3 kilowatts for 5% of water concentrations. So Advanced Cooling Technologies and Honeybee Robotics developed a preliminary thermal management system for lunar ice miner, which consists of a mechanically pumped fluid loop, a thermal corer, a cold trap tank, and a rotary unions. So in this work, we focus on modeling of the thermal corer to optimize its design. So further detail of the thermal corer or the entire system can be found in Honeybee Robotics paper reference here. The transient thermal model of the corer was developed using ANSYS Fluent, where the material properties of the icy soil are modeled as a function of temperature using user-defined functions, including specific heat, saturation pressure, mass fraction of ice, and thermal conductivity. The equations of the properties are listed here. So first, we take the temperature from fluent to calculate the saturation pressure, and then thermal conductivity, mass fraction, and specific heat. Then we use the new value of the properties to solve energy equations for the temperature in the next time step. So first, we simulated the full-length case, which is based on Honeybee Robotics core design. The size and boundary and initial conditions are listed here. We essentially implement a uniform warm temperature to the core from the outside and the inside of 400 K, while the initial icy soil was as 40 K. And because the hotter core will supplement the ice, and the water vapor will be extracted from the regolith. In this slide, we have a video showing the simulation of temperature A, mass fraction of ice B, and thermal conductivity C. So the thermal conductivity of the regolith inside the drill increased higher than the outside, leading to the temperature increase higher from the inside of the core, and that will supplement the ice on the inside of the core fully, roughly at 40 minutes. And so based on the initial mass fraction of 5%, the amount of water collected is 63.8 grams. Thus, the collection rate would be 0.1 kilogram per hour per core. Next, we perform lab-scale experimental testing to validate our model. We 3D printed a stainless steel thermal core with embedded channel of a length of 6 inches and tested. So as a result, we saw a total sublimation in around 9 minutes in both experiments and simulations, as shown in the temperature plot here. So therefore, we can conclude that the user-defined thermal properties of water and regolith can be used to predict the sublimation time. However, there is a difference in temperature increase before and after sublimations. And we think the reason is the difference in warm boundary conditions. So the model have a uniform warm temperature, while the experiments have warm water running inside the embedded channel. So further development in the future of the model will include the heat transfer of warm water inside the wall in 3D. So thank you for your time. Further questions can be directed to Quan Lin or myself, Quang Trong. And we also have one publications for this program as well. Thank you.